Hey guys, welcome to a little two-part series on efficiency in the context of the Diamond-Mortensen-Pissarides model. In this video, we're going to go through a planner's problem for this environment. Let's go. So this is what we're going to do. This is a short two-part video series which discusses the concept of Pareto efficiency in the context of the DMP model by working through a key result derived by Arthur Hosios in 1990. The way we do this is through the use of a planner's problem, which is the standard approach for discovering the conditions of Pareto efficiency in an environment which we seek to analyze. The goal of this exercise is to derive the planner's job creation condition. This is what we're working towards. And we will compare this condition to our job creation condition from the DMP model and ask under what conditions is efficiency achieved in the second part of this video series. We employ the use of the Hamiltonian, so if you're not familiar with this approach, see the series where I go through a few problems with this tool. So this is the planner's problem that we're going to go and look at, and the way we go and we read this is that our planner is looking to maximize a joint surplus by choosing the number of vacancies that he goes and posts in the market, and this is subject to our unemployed law of motion. So this is a very hard problem to work with directly, so we're just going to redefine this as follows, changing V to be the product of theta and U. Recalling that theta here is our labor market tightness, which is just the ratio of the number of vacancies all over the number of unemployed, and that's going to be maximized subject to our unemployed law of motion here. So first, the way we're going to go and solve this is write our Hamiltonian. Now this seems like a little bit of an awkward way to go and write it, because usually you go see a plus sign there, but here we're just going to go and change this to a negative sign, and the first order conditions sign is going to change accordingly. So we're going to take our first order condition with respect to our labor market tightness and with respect to our unemployed workers. So rearranging our first order condition, we go and we get the following, right? Working through this algebra here, and we're going to go and define this term eta theta, which we'll go and discuss its meaning in the next video. That's going to be equal to theta q prime theta all over q theta, right? Putting a negative sign in front of all of that. Thus, we go and we derive this third equation, which we are going to keep in mind. Taking the natural logs of this equation and differentiating with respect to time, we go and we obtain the value for our multiplier in motion. That is going to be equal to negative r, right, times lambda t. Now, using our definition of this lambda t dot, we're going to go and sub it into equation 2. So our first line here is just our second first order condition, and this next line is just us subbing that in there. With a little bit of algebra, we can go and derive what this lambda is here. We also note from 3, right, keeping that in our mind. If we rearrange that and solve for lambda t, we also get the following result. By going and taking these two results and equating them to each other, we can obtain our planner's job creation condition defined as follows right here. So we got to our planner's job creation condition. In our next video, we're going to discuss how this condition relates to our competitive case in the standard DMP model and discuss what is our condition of efficiency there. I will see you in the next video. Take care.